Welcome everybody to this week's discrete optimization talks. Today we have Carla and Christian speaking on topics at the intersection of integer programming, combinatorial optimization, and applications. So we'll start first with Professor Carla Michini from Industrial and Systems Engineering at the University of Wisconsin at Madison. Carla received her PhD in operations research from Sapienza University of Rome in 2012. And after that, she was postdoc at ETH Zurich and at Wisconsin Institute of Discovery. Carla's research is focused on theory and applications of combinatorial optimization. Currently, she's most interested in the study of congestion games and simplex path of lattice polytopes. And today she's going to tell us more about recent work in congestion games. So Carla, please take it away.
Oh, thank you so much for the nice introduction. Hello, everybody. So thank you actually for inviting me to give a talk in the DOT series. I'm really honored. So today I will be presenting a work with my PhD student, Bainian Hao. And this is about network congestion games and the study of Price of Anarchy. So let's get started. So first of all, I want to define what network congestion games are. So supposed to have a network G and N players. Now, every player has an origin node Si and a destination Ti, and every player I wants essentially to select a shortest path from Si to Ti. But unlike in a shortest path problem, the edge costs are not constant, but they are defined by a non-decreasing delay function. So for every edge, we have a non-decreasing delay function DE that takes in input the number of players using the edge and gives in output a non-negative number. So this models the effect of congestion. So intuitively, the more players are using an edge, the higher is the cost of the edge. So when we are in a strategy profile, which is a collection of paths, one for every player, again, every player pays for a path depending on the edge selected in the path and depending on how many players are using the edge. And the game is called the symmetric if every player has the same origin and the same destination. And actually, in this talk, I will be focusing on symmetric network congestion games. Now, one of the most popular and well-known solution concepts for games in general is the one of pure Nash equilibrium. So informally, a pure Nash equilibrium is a strategy profile where no player has an incentive to unilaterally deviate. So in this case, no player can find a path. So when we are in a, when we are in a pure Nash equilibrium, no player can find a path with lower cost, provided that the other players stick to their strategies. So this is the concept of pure Nash equilibrium, and I want to make sure that to point out that this is not the same as a Nash equilibrium, also called mixed Nash equilibrium. So in a pure Nash equilibrium, every player has to specify exactly the strategy chosen. In a mixed Nash equilibrium, instead the players specify essentially a probability distribution on the strategy set. And pure Nash equilibria are not guaranteed to exist in general, but they do exist for the class of congestion games. And actually for network congestion games that are symmetric, we can find them in polynomial time. Okay, so this is about pure Nash equilibria, and another interesting concept is, relevant concept is the concept of social optimum, which essentially is a strategy profile that minimizes the total cost of the players. So you minimize the sum of all the players' costs. Let me give you an example. So here we have a network. The game is symmetric, so all the players go from S to T. We have 3 players, and for every edge, we have a delay function, which is actually affine. So let's look at how a pure Nash equilibrium can look like. So here, the blue player takes this path, and you see it, the green and red players select their strategies as well. So on the top edges, we actually have 2 players, and on these edges over here, instead, we have only 1 player. So every player that selects a top edge pays 2, and every player that selects, for this edge, and this edge instead costs 1 for every player that selects it. So in the end,
Carla, we don't
yes.
see your cursor. At least I don't see your cursor. I don't know if you're
you
trying
cannot
to point.
see it. Oh, okay. What about now?
Oh, now I see it. Now I see it.
Yes, the pointer is useless. This is the news. Okay, but I'll use my mouse. So I hope that things were not too unclear up to now. But yeah, I was saying that this edge has cost 2 because it's used by 2 players, and this edge has cost 1 because it's used by 1 player. So every player in this solution pays 5. Right? 2, for example, the blue pays 2 plus 1 plus 2. So every player pays 5, and no player can find a path with a lower cost. So this is a pure Nash equilibrium, and the total cost is 15. Now there is another strategy profile with lower cost, which is this one. So now the red and green players pay 3 each, and the blue player pays 5. So the total cost is 11. So as you can see, there can be a gap between the social cost of a pure Nash equilibrium and the minimum social cost that we can achieve. And so we want to measure the inefficiency of pure Nash equilibria. So what I want to remark is that pure Nash equilibria are interesting because they represent stable outcomes of the game, because nobody has an incentive to deviate. However, they could be bad in terms of minimizing the social cost, and instead the social optima are very good in terms of social welfare, but they could be unstable. Now in the previous example, if you can check that actually this social optimum is also a pure Nash equilibrium, but this is not necessarily the case. So this is why there is this trade-off essentially between stability and minimizing the social cost. And 2 standard measures to measure the inefficiency of pure Nash equilibria are the price of anarchy and the price of stability. Essentially, in the price of anarchy, we look at the worst case scenario. So we look at the pure Nash equilibrium with highest social cost, and we look at the ratio of this cost of this pure Nash equilibrium over the minimum social cost. And instead, the price of stability is like a best case scenario. So we look at the smallest ratio between the cost of a pure Nash equilibrium and the cost of a social optimum. So in the previous example, the price of anarchy is 15/11, and I've not written it, but the price of stability would be 1, because the social optimum here turns out to also be a pure Nash equilibrium. Are there questions about these?
Not at this point. I think everything is pretty clear. Yeah.
Okay, so in this work, we are studying the price of anarchy. So what do we know about the worst case price of anarchy in network congestion games? So there are a lot of, so the literature is really rich, and there are a lot of variants of network congestion games that have been defined. So for example, there is a distinction between non-atomic and atomic games. So in non-atomic games, players essentially control a negligible amount of flow, and they're actually not able to affect the other's decisions. So in this case, the worst case price of anarchy is rho of D, so it's characterized based on the class D of delay functions that we are using, and it has been proven by Rovgarden that this worst case price of anarchy is actually independent of the network structure. So network structure has no impact when we consider non-atomic games. And just a remark that if we look at the class of affine delays, rho of D is 4/3. If we look at the class of polynomial delays with highest degree P, then rho of D is a function that asymptotically grows as P over logarithm of P. So what about atomic games? Is there any impact of structure in that case? And now I have to make another distinction between weighted and unweighted games. So in unweighted games, all the players have the same effect on congestion. In weighted games, instead, every player has a weight and can affect congestion of the edges in different ways. So when we look at weighted games and polynomial delays with highest degree P, what is known is that for general networks, the worst case price of anarchy grows as this function phi p to the p plus 1, where the basis of this function is phi of p, which grows as p over logarithm of p. So in other words, the price of anarchy, the worst case price of anarchy grows exponentially, is an exponential function, and phi of p, which is the basis of this exponential function, is sublinear in P. But the interesting thing is that this worst case price of anarchy is already achieved in very, very simple networks that only have parallel links. So also for atomic weighted games, it seems that network structure doesn't have really much of an impact. So our focus is then on atomic unweighted games, and we study two cases: the case where the delays are affine functions and the case where the delays are polynomial functions with highest degree P. So in the affine case, what is known is that for arbitrary networks, the price of anarchy, the worst case price of anarchy is 5/2. And when we look at a specific class of extension parallel networks, this worst case price of anarchy goes down to 4/3. So definitely there is some impact of structure. By the way, extension parallel networks are networks that essentially you construct starting from a single edge, and then you can do compositions in parallel and also in series, but you can only compose an extension parallel networks with an extra edge. So extension parallel networks are a subclass, a proper subclass of series parallel networks. So it is kind of natural to ask what happens for series parallel networks. And for affine delays, we know that this upper bound on the price of anarchy does not hold. In fact, Fotakis constructed an instance where the price of anarchy is 15/11, which is exactly the one that I have shown before. Okay, so this is about affine delays, and instead for polynomial delays with highest degree P, we know that again in arbitrary networks, the worst case price of anarchy is in this range, so it's pretty similar to the function that I described before, so it's exponential. And instead, for extension parallel networks, the price of anarchy is rho of d. This was proven by Fotakis, which, remember, is in theta of p divided by logarithm of p, so it's sublinear. So there is a huge, you can really see when you consider polynomial delays that there is quite a huge difference in the worst case price of anarchy. So definitely it seems that there is an impact of network structure. So our goal is to understand better the case where the network is series parallel. So we relax a little bit the network topology by going from extension parallel to series parallel networks.
Carla, quick question. In
Yes.
the toy example that you showed earlier, in which category does it fit?
This is a series parallel graph.
Okay, atomic unweighted.
Atomic unweighted symmetric. Yes. Okay. So there are 3 players and also with affine delays. Yes. And you see the price of anarchy is 15/11. So definitely, this is actually the example that was shown by Fotakis. So we have a lower bound on the worst case price of anarchy that is 15/11. Okay. Yes, so so these are our results. So again, we look at we study atomic and weighted symmetric network congestion games, and we look at series parallel networks. Now, when we look at affine delays, we can improve the best known upper bound of 5/2 that actually holds for arbitrary networks, and we can improve it to 2. And on the other end, we can improve the best known lower bound, that is the example that we just saw, to 27/19. When we look at polynomial delays with highest degree p, we can improve the upper bound to 2 to the p plus 1 minus 1. So essentially, we can improve the basis of this exponential function from something sublinear to a constant, which is 2. And we can improve the best known lower bound. So this is the essentially the worst case price of anarchy for extension parallel networks. We can improve it to a lower bound that is in omega of 2 to the p divided by p. So as this essentially tells us that the worst case price of anarchy, when we go from extension parallel to series parallel networks, goes from sublinear to exponential. But still, the worst case price of anarchy is still better than in arbitrary networks. So these are our results. And in the remaining part of the talk, maybe I'll try to give you some ideas about how we obtained it, obtained them, sorry. So again, we want to study series parallel networks, which are an more general class than extension parallel networks. And the approach that Fotakis developed for extension parallel networks cannot be easily generalized. So in particular, there are two very bad news. So first of all, we know that when we have n ST paths, we can easily define an ST flow value n, these all in general graphs. And conversely, when we have an ST flow value n, we can decompose it into n ST paths. Now, the nice property of extension parallel networks is that actually this decomposition is unique. So this essentially says that there is a one-to-one correspondence between the strategy profiles and the n-valued flows and valued ST flows, because there is only one way that I can decompose the flow into an ST paths. But unluckily for us, this property does not hold anymore in series parallel networks. So this is the first obstacle that we need to overcome. The second obstacle is that, I mentioned that network congestion games always admit a pure Nash equilibrium, and this is because these games are potential games. In other words, there exists a function called the potential function that you can define over all the strategy profiles of the game and that you can minimize. And there is a one-to-one correspondence between the local optima of this potential function for some neighborhood structure and pure Nash equilibria. So these also in general for congestion games, local optima, pure Nash equilibria are the local optima of the potential function. But actually in extension parallel networks, every pure Nash equilibrium is a global minimum of the potential function. So there is no local minimum essentially. And this implies that the price of anarchy and the price of stability coincide. So this is a very strong property of extension parallel networks that was used to characterize the price of anarchy. But unluckily in series parallel networks, this is not true anymore. So there are pure Nash equilibria that are local optima, but not global optima, and as a consequence the price of anarchy can be bigger than the price of stability. So this is the second bad news for us. So hopefully I can give you some idea about what to do with this. So to study the price of anarchy, we will essentially compare a flow F that is induced by pure Nash equilibrium and a flow O that is induced by a social optimum. And actually we study the difference O minus F. So this difference essentially defines a collection of cycles in our graph of simple cycles, and you can associate to each of these cycles two paths. Let me call them Ci plus and Ci minus that go from a node Ui to a node Vi. maybe let's look at the picture here. So let's say that this is F, the flow induced by the pure Nash equilibrium, and this is O, the flow induced by a social optimum. I look at the difference, you see we can define a cycle, you know, this difference defines a cycle, and from the cycle we can associate to the cycle two paths. In this case, they go from S to T. So Ci minus is a path where actually F is bigger than O, so there is a typo here actually, and instead Ci plus is the path where O is bigger than F, right? So here in the social optimum we have one player, and instead in the pure Nash equilibrium we had 0, and instead on these red edges we had 2 players in F and 1 in O. Okay, so this is the basic structure that we will be using. And the good news is that in extension parallel networks, these two paths, Ci plus and Ci minus, are always internally disjoint, which means they only intersect on the start and end node. And luckily, this still holds for series parallel networks. If you relax the series parallel requirement, this would not hold anymore. So we can still use these. Okay, so when we look at the affine delay functions, essentially we can use our starting point is using this inequality that was proven by Fotakis. In this inequality, you see that there is this expression delta FO that essentially is defined based on the cycles C1 up to CH. And for extension parallel networks, Fotakis showed that this delta here is always less than or equal than 0. So by exploiting this, you can immediately get that the cost of F is less than or equal than 4/3 the cost of O. So the price of anarchy is at most 4/3. But for series parallel networks, it's not true anymore that delta is less than or equal than 0. So we have to spend a lot of efforts to actually prove that this delta is less than or equal than 1/4 cost of F. And then once you have this, you simplify this expression and you get that the price of anarchy is at most 2. So essentially the main building block of our proof is to show this inequality over here. I don't know if I have a question, so, oh, okay, I have 5 minutes, okay. So the main tool that we use is a decomposition of flows that we call greedy decomposition. So given a flow F, the flow induced by a pure Nash equilibrium, we essentially decompose it into n paths by first looking at the most expensive and then at the next most expensive until we get to the cheapest path contained in F. So we define this decomposition and we can prove some nice properties of this decomposition, which maybe now I don't have the time to explain, but we can prove a key property that will actually imply that delta is less than or equal than 1/4 cost of F. So again, the main tool is the definition of this greedy decomposition and finding some key properties of this greedy decomposition that can help us. When we look at polynomial delays, instead, we define a function y that depends on the specific class of delay functions that we are considering. So this is the definition of y. And then the proof structure is the following. We look at an arbitrary decomposition of O. This could be any decomposition. And then we first make an assumption. We first assume that there is some path Ci plus that actually goes from S to T. So if this is true, we can prove that the cost of each one of these paths is at most the average cost of a player in the pure Nash equilibrium divided by y of d. So when we have this inequality over here, we can just, so we have one such inequality for every path of the decomposition, sum them up, and you obtain that cost of O is less than or equal than, cost of F divided by cost of O is greater than or equal than y of d. Which actually implies our result. And then we relax this assumption that there is this Ci plus from S to T, and we need to use one property of series parallel graphs, one laminarity property, to actually prove the same result in general. So essentially for polynomial delays, the analysis is different. We use this function and we use a laminarity property of series parallel graphs. So I don't think that I'm not sure I have time to go over the lower bound. So maybe I can just skip to the conclusion. So in the end, we have studied the impact of network structure in series parallel network congestion games in the unweighted atomic case. And we looked at two cases, affine delays and polynomial delays. So we have improved the current, the best known lower and upper bounds in both cases. And really the take-home message is that there is still a significant impact of structure. So the efficiency of the pure Nash equilibria, is still, the inefficiency is still limited by the network structure. But this inefficiency degrades pretty quickly when we relax the network structure from extension parallel to series parallel. So this, I guess, concludes my talk. So thank you for your attention.
Okay, great. Thank you, Carla.
Yes.
Folks in the audience, if you have a question, please feel free to type it in the chat or just unmute and ask. So we do have a couple minutes.
And there's also
clapping. Yes,
and there will also be time afterwards in the breakout rooms to kind of have a discussion, more one-to-one setting, or one-to-many, but not so many.
Yes, exclusive. Carla, I had a general question about why do people look at these specific forms of delay, the affine and polynomial? Is there a practical reasons why these are the interesting ones?
I think that it just makes sense to to make some assumption on the delays and just study what impact this assumption can have. So no, I don't have an answer for you. I mean, I guess that it's probably relevant in many applications, but I'm not an expert in applications, so sorry, I cannot really provide an example.
Okay. Yeah, I was just wondering. Yeah.
Yes.
Carla, I have a question too.
Yes.
So your proof requires this upper bound on delta FO being 1/4 of the cost of F, right? And that somehow is really tied to the fact that the series parallel has this vertex disjoint paths that you can break things up into, and then also has a few other properties that you're using of series parallel. Is that correct?
Yes.
So basically my question is, if you're going to try to extend things for more general network structure, do you see a path forward with your proof technique, or do you have to use something completely different?
So I'm not sure. So there could be some way of, kind of look at how much these cycles overlap between them, and, maybe assuming that the overlap is bounded in some way, then maybe you can use this parameter to bound the price of anarchy. I don't know if that could be a path. Or another way to go could be, but it's not clear to me how to proceed, could be to look at the 3-width parameter. So here we are looking at two terminal series parallel graphs. When you consider series parallel graphs in general, these are graphs with 3-width 2. And so you might try to extend, the next maybe kind of network structure to look at could be graphs with 3-width 3, for example.
And then another question that I was kind of curious is, this is symmetric. Is there anything that can be said about like non-symmetric or partially non-symmetric or something?
So yes, so okay, 2 reasons for considering symmetric games, but I'm also curious about investigating the non-symmetric case. But so first, in the symmetric case, we can compute a pure Nash equilibrium in polynomial time. Instead, for asymmetric, it is PLS complete. And also there is a work showing that for atomic unweighted games, essentially in arbitrary networks, there is no gap between symmetric and asymmetric games. So there is an indication that assuming symmetry should not have an impact. However, I think this has been proven for general networks. So I'm not 100% sure that even when you restrict the network structure, you know, you cannot, the price of anarchy essentially remains the same when you look at asymmetric networks. So this is something actually I'm curious about. I'm not sure it will have much of an impact, but yeah, I would still, you know, I would like to know more about that.
Makes sense. Thank you.
Thanks.
Okay. Good job, Alex. You stole Merve's question.
Merve's question.
I'm sorry. I should have said that people can unmute themselves too. That was probably for the next talk. You're allowed to unmute yourself, Merve, and you'll get first priority. So, oh yeah, that's Elias. Please go ahead.
No, I'm good.
Okay. Well, Carla, thank you very much.
Yes, thank you.
Thanks, Carla.
Yes.